Hello students. In my last class we dealt some of the topics related to ray optics and we completed the chapter. Today we will see the numericals related to ray optics. Here we have a first numerical on the screen. The numerical is based on the refractive index and the refraction. Here we have the numerical. What is the speed of light in glass of refractive index? 1.5 given that speed of light in water is 2.25 into 10 to the power 8 meter per second and refractive index of water is 1.3. Here in this question, so that ray is coming from water and it enters into the glass medium. Refractive index of the glass is given, mu 2 is equal to 1.5 and the refractive index of water is given, mu 1 is equal to 1.3, and also the speed of light in water is given, speed of light in water V1 is equal to 2.25 into 10 to the power 8 meter per second. Now we have to find out the velocity of a light in the medium of glass, that is V2 is equal to question mark. So here we assumed as a V1 as the velocity of a light in water and V2 is the velocity of a light in glass. Now according to Snell's law we know that refractive index is equal to sin A by sin R, or in other words we can say that the refractive index is the ratio of velocity of a light travelled in a vacuum to the velocity of a light travelled in a particular medium, or for this case the refractive index of glass with respect to water can be written as velocity of a light travelled in water to the velocity of a light travelled in glass. So we can write like this, mu 1 multiplied by velocity of light in water which is V1, this will be equal to mu 2 multiplied by V2. Now here we have to find out the velocity of light in glass medium. So V2 is equal to mu 1 multiplied by V1 divided by mu 2. Now we have to substitute the values of mu 1, mu 2 as well as V1. Here mu 1 is 1.3, so I substituted here, multiplied by V1 is 2.25 into 10 to the power 8 divided by mu 2 is 1.5. So this further can be written as 13 multiplied by 2.25 into 10 to the power 8 divided by 15. So here we will get 13 multiplied by 2.25 divided by 15. So now we have to multiply 13 and 2.25 which gives 13 multiplied by 2.25 into 13. So 3 5s are 15, 1 remainder, that is 6, 1 7, 3 2s are 6, 5 2 2, 5 12, 1 9 2. So we are getting 2925. So this can be written as 2925. After two decimals, two numerals we have a decimal, so it can be 29.25 multiplied by 10 to the power 8 divided by 15. On simplification of this we will get the value which is equal to 1.95 into 10 to the power 8 meter per second. We see here that the velocity in glass comes out to be 1.95 into 10 to the power 8, which is lower than the velocity of a light travelled in water medium. This indicates that as the refractive index increases, the velocity of a light decreases. Next we have a second numerical. The numerical on the screen is what is the apparent position of the object below a rectangle glass slab of 6 cm thick, comma, if the layer of water 4 cm thick is on the top of glass. Given refractive indices of glass and water are 3/2 and 4/3 respectively. Here we have to find out the apparent position of the object below a rectangle slab. A rectangle slab is there here. We have a rectangle slab here. So an object is placed below rectangle slab. Here we can draw a normal. Let us suppose here we have drawn a normal. So the thickness of this glass is 6 cm. Here we have a thickness. The thickness of the slab is 6 cm. A layer of 4 cm thick is on the top of glass. Here we have another layer which is of water. So this is water and this one is glass. The refractive index of glass is given, which is 3 by 2. Refractive index of water is given, it is 4 by 3. Now we have to find out the apparent shift in the position of object. Now suppose that a beam of a light arises from this point, here it will move like this, it faces one of the interface which separates water as well as glass medium. Now it will undergo refraction process. Let us suppose I be the angle of incidence. When it enters into second medium, it will move like this, it will deviate away from the normal because of low refractive index of water, it will move like this. So when we produce here, we get an apparent position of the object in the glass medium. So that apparent position can be determined. Let us determine the apparent position of an object in the glass medium. The formula for determination of apparent position is given by apparent position is equal to real position divided by the refractive index. So apparent position for the case of glass is given by real position here is 6, that is the actual depth of an object in a glass, 6 divided by refractive index of glass, which is 3 by 2. So this can be written as further, 3 get cancelled out, we have 2 into 2 equal to 4 centimeter. So we got apparent depth of an object in the glass is 4 centimeter. Now we have to find out the apparent position of object in water. So apparent position of object in water can be determined by knowing the refractive index as well as thickness of water. Here the thickness of water is given by 4 centimeter. So apparent depth in water is given by, or the apparent position of an object is given by real position here is 4 centimeter, 4 divided by the refractive index of water is 4 by 3, this can be 3 centimeter. So the total apparent position, that is the depth of object from the upper surface of water is given by the total shift produced by glass as well as water, which is equal to 4 plus 3 equal to 7 centimeter. So this is the apparent position of an object. Now the actual depth will be equal to, so or shift is equal to real depth minus apparent depth. Here the real depth is the total sum of both the thickness, that is 4 plus 6, which is equal to 10 centimeter. 10 minus apparent depth, what we calculated, which is the sum of the apparent depth produced by both glass as well as the water, that is 7. So here the shift produced is 3 centimeter. So we find that the final shift produced by the system of two mediums is 3 centimeter. It indicates that when a layer of water is placed over a glass and an object is placed just below the water, then when it is seen from the upper surface of water or from the air medium, we find that the body appears to be somewhere different place from its actual place. That is, from the actual place it is 10 centimeter, it is at a depth of 10 centimeter. Now we will see this object at 3 centimeter difference between real as well as apparent depths. That is, there is a shift between actual position and the real position of an object, which is equal to 3 centimeter. So here in the figure, glass medium produces an apparent depth of 7 centimeter, that is, object will be seen at a distance of 7 centimeter from the surface, and water produces shift of total apparent depth is 7 centimeter, that is, in a glass medium the shift produced is 4 centimeter, that is, the object will be seen at a distance of 4 centimeter from the surface of glass. Similarly, this apparent object which is formed will act as an object for the water medium, and finally the image will be formed at O double dash, which is at a distance of 7 centimeter from the top, that is, the shift produced here is 3 centimeter. From the original position and the new position, the difference between these two is 3 centimeter. Now in previous question we saw the normal shift, now we will see the lateral shift. Here we have a question: a ray of light is incident at an angle of 48.6 degree on one face of a rectangular glass slab of thickness 10 centimeter and refractive index 1.5. Calculate the lateral shift produced. Given sin 48.6 degrees is equal to 0.75 and sin 18.6 degrees is equal to 0.318. Now we will try to find out the solution of this question. A ray of light is incident at an angle of 48.6 degree on one of the face of rectangular slab. Here we have a rectangular slab. At one face, the ray entering at one of the face and making an angle of 48.6 degree. It enters into the glass medium like this. Because its refractive index is higher, therefore it bends towards the normal. Let this angle be R. Now, if no glass medium is there, then the beam has to pass as it is like this. Because of the presence of glass, beam bends towards the normal. It deviates from its actual path. Therefore, after emerging from the glass slab, both the rays will move parallel. So there is a perpendicular distance between these two. This perpendicular distance is said to be as lateral shift. Now we need to find out this lateral shift. Here sin 48.6 degree is there, and then angle R is there. Let us suppose that this is O. Produce this to meet the other side of a glass slab at A. So it is BC, and let us suppose the lateral shift be D. So this angle is equal to, if the I is the angle of incidence, then this angle can be written as I minus R. So here it is thickness T. In the question, thickness T is given as 10 centimeter. T is equal to 10 centimeter. So let us find out the value of D. Now by using Snell's law for the surface which separates air as well as glass, we can write like this: sin I by sin R is equal to refractive index mu. The refractive index of a glass given here as 1.5. So in place of mu you can take 1.5, and sin I, the value of I is 48.6 degree divided by sin R is equal to 1.5, and the value of sin 48.6 degree is given in the question, which is 0.75. So sin 48.6 degree is equal to 0.75, it is given in the question. So we will substitute that value here. On substituting, we get 0.75 divided by sin R is equal to 1.5. So further this can be written as sin R is equal to 0.75 divided by 1.5. So this can be written like this: 7.5 divided by 15. Cancellation of this gives 0.5. So we got sin R is equal to 0.5, or R is equal to sin inverse of 0.5, which is equal to 30 degree. So we got R is equal to 30 degree. Now we need to find out OB the hypotenuse. In triangle AOB, cos R is equal to OB divided by, cos R is equal to OA divided by OB. Now the value of R is 30 degree, so it is cos 30 degree is equal to OA, which is T divided by OB. The value of T already given in the question, which is 10 centimeter. So cos 30 degree is equal to 10 divided by OB, or OB is equal to 10 divided by cos 30 degree. 10 divided by, we know the value of cos 30 degree, which is root 3 by 2. So here we can write root 3 by 2, or OB is equal to 10 multiplied by 2 divided by root 3. This can be written as 20 divided by root 3. After rationalization, it gives 20 root 3 divided by 3, which is 6.66 root 3 centimeter. So we got the hypotenuse side as 6.66 root 3 centimeter. Now, after this, take the triangle OBC. In triangle OBC, we have sin I minus R equal to opposite side by hypotenuse, that is D divided by OB. We already calculated the value of OB, we will substitute it there. Our aim is to find out the value of D, the lateral shift. Now, sin, the value of I is 48.6 minus value of R is, so we calculated, which is 30 degree. So here we will substitute it. So this will be D divided by OB, or sin 48.6 minus 30 degree is 18.6 degree equal to D divided by OB, or D is equal to OB multiplied by sin 18.6. The value of OB is 6.66. We will substitute here. So on substitution, it gives 6.66 root 3 multiplied by sin 18.6, which is given in the question. Sin 18.6 is 0.318. We calculated the value of OB, which is 6.66 into 1.732. Multiplication of these two gives 11.54. We substituted there. After multiplication of these two terms, we get D is equal to 3.66 centimeter. So the lateral shift produced in this question comes out to be 3.66. Now we have a next question here. A diverging lens of focal length 15 cm forms an image 10 cm from the lens. First off, calculate the distance of the object from the lens. What is the linear magnification of the image? So here we have a diverging lens. So let us draw a diverging lens here. A diverging lens is there. So this is diverging lens. It has principal axis. Now, its focal length is given as f is equal to 15 centimeter. Now we know that for a diverging lens the focal length is negative, therefore this can be written as minus 15 centimeter. So f is equal to minus 15 centimeter, and an image of 6 centimeter from the lens. Object is placed at some point and the image is forming from the lens at a distance of 10 centimeter. So V is equal to 10 centimeter. Now for the case of concave lens or diverging lens, the image comes out to be virtual. Therefore, V is to be taken as negative. Now we need to find out the linear magnification M. For finding the linear magnification M, we must need the value of U. So let us find the value of U first. So from the lens equation, we have 1 by F is equal to 1 by V minus 1 by U. So here V is given, F is also known, U can be determined. 1 by U is equal to 1 by V minus 1 by F. Now substitute the value of V here, 1 by minus 10, then minus 1 by F. Value of F is minus 15. So this can be written as minus 1 by 10 plus 1 by 15, or you get 1 by U is equal to, so this can be, you can take common denominator here, we get minus 3 divided by 30, then plus 2. So 1 by U is equal to minus 1 by 30, or U is equal to minus 30 centimeter. So we got the value of U is equal to minus 30 centimeter, and the magnification formula here is magnification is equal to V divided by U. The value of V here is minus 10 centimeter divided by U is minus 30 centimeter. So it comes out to be 1 by 3. So magnification here is comes out to be 1 by 3. So let us draw the ray diagram. We have object at some distance which is at 30 centimeter. So let us say here we have 30 centimeter and object is there. So U is equal to 30 centimeter. Beam will move towards the lens which arises from the object. Because of diverging lens, it deviates from its actual path. The deviated or diverged beam move like this. When we produce it, we get somewhere image here which is at a distance of V equal to 10 centimeter. So this is what we determined in this question. The factors what is asked in the question is magnification as well as U. F is given 15 centimeter. For diverging lens, F is negative, therefore we took F is equal to minus 15 centimeter, and V is given here as 10 centimeter, and for diverging lens, image is always virtual, that's why we took V equal to minus 10 centimeter, and we have to find out the magnification M as well as U is U. So for that purpose we determined the value of U first, and we got U is equal to minus 30 centimeter. It indicates that the object is placed before the diverging lens, and the magnification M is equal to V by U, which is comes out to be 1 by 3. We have a next numerical here. Light from a point source in air falls on a convex spherical glass surface of refractive index mu is equal to 1.5 and radius r is equal to 20 centimeter. Calculate position of image when the light source is at 1 meter from the glass surface. So here we have a light source. Let us suppose O be the light source which is at a distance of 1 meter from the spherical surface. So this will act as an object distance. U is equal to 1 meter. So this can be 100 centimeter. So object is located, that is light source is located before the convex surface, therefore this can be taken as minus. So U is equal to minus 100 centimeter. Next here is the refractive index of the convex surface is given, mu is equal to 1.5. So beam of a light strikes at the convex surface, it undergoes refraction making an angle of incidence with the normal. When it enters into the second medium, that is denser medium, it bends towards the normal making an angle R. So other things which is given in the question is radius R is given, R is equal to 20 centimeter. So we need to calculate the image V is equal to question mark. So V we have to find out. So things given in the question is U is equal to 1 meter, R is equal to 20 centimeter, R the radius of a convex surface falls towards the right hand side, that's why this can be taken as positive. We need to find out. So we need to write the formula that connects all these factors. We know the formula here is mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. So here mu1 is this one, the rarer medium which is equal to 1, and denser medium have the refractive index 1.2. So in place of mu2 I am substituting its value. We need to find, so let it be minus 1 divided by U, the value of U is minus 100 centimeter, we will put here, so equal to mu2 1.5 minus 1 divided by R, the value of R is 20 centimeter. So we get 1.5 divided by V plus 1 by 100 equal to 0.5 divided by 20. So 1 by 100 can be taken towards that side. We get 1.5 by V is equal to 0.5 divided by 20 minus 1 by 100. So 1.5 by V is equal to, multiply this with 4, we get 0.5 into 5 divided by 100 minus 1 divided by 100, we get 1.5 divided by V is equal to 2.5 divided by 100 and then minus 1. So 1.5 divided by V is equal to 2.5 minus 1 is 1.5 divided by 100, 1.1.5 cancel out and we get finally V is equal to 100 centimeter. So we got the image distance as 100 centimeter and object distance is also equal to 100 centimeter. It means that the object is forming image on the denser medium at a distance of 100 centimeter from the spherical surface and object is placed at a distance of 100 centimeter before the spherical surface. Here we have a next question. Two thin lenses are in contact and the focal length of the combination is 80 centimeter. If the focal length of one of the lens is 20 centimeter, then what would be the power of other lens? So here two thin lenses are given. So let us suppose this is first lens and second lens is also there. Maybe it is concave or convex, we do not know, but here it is given that the total focal length f is equal to 80 centimeter and then focal length of one of the lens is f1 is equal to 20 centimeter. We have to find out the power of second lens, let us say P2, which is equal to question mark. Now from the formula of combination of lenses, we know that the reciprocal of focal length will be equal to sum of the reciprocals of focal lengths of individual lenses, which is equal to 1 by f1 plus 1 by f2. 1 by f is equal to, in place of 1 by f we can substitute its value 1 by 80 equal to 1 by f1 is 20 then plus 1 by f2, or 1 by f2 equal to 1 by 80 minus 1 by 20, 1 by f2 equal to, this can be written as 1 by 80 minus 4 by 80 or minus 3 by 80. So we got power P2 is equal to minus 3 by 80 per centimeter. So this can be converted into meter. 3 by 80, 1 divided by, multiply with 100 on both numerator and denominator, we get P2 equal to minus 3 divided by 80 multiplied by 100 to 100 centimeter is 1 meter. So we get 1 by meter and 1 by meter is diopter. So P2 equal to minus 3 into 100 divided by 80 diopter. So 0 0 cancels. So this gives minus 30 divided by 8, which is equal to 3.24667 diopter with negative sign. So the next lens is diverging lens whose power comes out to be minus 3.7 diopter. These are the few numericals we shown today. In our next class we will see some more numericals. Till then I hope that you all will practice the numericals and try your level best. Thank you.